Hi, and welcome to this demo. This is a breakout from our AI webinar series, Navigating AI Risks. And at this point in the presentation, we were talking about open source tooling, both from Microsoft and the larger community, that you can use to retrain models, to reduce bias, to provide documentation for transparency reasons. And so what we're going to do is we're going to build upon our scenario. Now, if you recall, in the session, we were talking about a loan pre-approval system. This pre-approval system would take information from a customer and then decide if they were a high earner or a low earner. And based on the response or the prediction, it would be able to suggest specific products based on the results. Now, what we're going to do is take a look at using FairLearn initially. And so what we're going to do is demonstrate how we can use FairLearn to produce what we call an unmitigated model. And then we can show off potential bias. So what I'm going to do is share this code with you. And we will walk through this, not line by line, but in enough detail for you to understand what's happening. So at the beginning, we start with some essential imports. We're going to be importing libraries for data handling, machine learning, and fairness evaluation. So we are grabbing matplotlib and pandas. Now these help us with plotting and data structures. We have sklearn, which gives us the tools for building and evaluating machine learning models. And then we have FairLearn. This is our key library, and this is for fairness analysis. So it lets us both assess fairness and mitigate bias. The next thing we're going to do is grab the adult census dataset. Now, the adult census dataset is purely for demonstration purposes. It is a subset of the census data from the entire US. Now, it's not all of the data, it's a subset. It's around 30 to 40,000 records dating back from 1994. So it's obviously not representative of modern times, but it gives us a really good baseline to show how bias might creep in. Now, what we're actually looking to do here is we're looking to predict if somebody earns more than $50,000 a year. Now, we convert this into a binary value if they earn more than 50,000, otherwise it's a 0. Next, we declare our sensitive features. Now, our sensitive features, in this case, is called sex. We'll use it later to evaluate fairness, but we remove it from the features used to train the model to try and avoid bias, which is right here. Now, the next part, and this is important, is scaling. Now, we scale the numerical features so that they're all on a similar range. Why? Because features like age or hours work can have very different value ranges. And if we don't scale them, the model might overemphasize one feature just because it has bigger numbers. Then we encode the target. So we convert our target variable. Now, income above or below $50,000, remember, we convert that into numerical values so that the model can work with it. It's already binary, but encoding this keeps things consistent and it avoids any format issues later on. Next, we split our data. Now, we're going to split the data into training and test sets. Importantly, we also split the sensitive attribute sex so that we can assess fairness later. We'll use what we call stratification to make sure that both groups, those earning above and below, are equally represented in both groups. Okay, so what we'll do next is let's run this. And what we should expect to see in a moment is some interesting information from FairLearn. Okay, so what are we actually looking at? You'll see that we had just shy of 20,000 records that we used for training and testing. Now, the important part really is at the bottom here. You'll see this property called selection rate. We have female and male. Now, 0.07 actually means that 7% of the time, females were identified as high earners, whereas 25 or nearly 25.5% of the time, males were predicted as being high earners. So this is what we call an unmitigated model. And it means basically that we haven't applied any fairness constraints yet. And you can see that there's a clear gap. Male applicants are predicted as high earners around 25% of the time, female applicants just under 8%. Now that's nearly 18%. That's nearly an 18% gap between both groups. Now, we've already done the right thing by declaring sex as a sensitive feature, and we've split the data properly for training and testing, but clearly that's not enough on its own. And so we can move on. Let's go to the next part of our demo. Now, this is the same code, but what you'll notice at the bottom here, let me just find my spot, sorry. Here we are. Is that we are using something called grid search. Now, grid search is a tool that tries out many different versions of the model to try and find the one that best balances two goals. The first goal being accurate and the second being fair. So if you can imagine a chef, and a chef has been given a set of ingredients and has been told to make a recipe. And the chef is allowed to tweak the ingredients X number of times to try and make the perfect outcome. And that's essentially what grid search is doing. Now, the other thing that we're doing that's really important to point out is that we're setting a constraint. Now, the constraint is what we call the demographic parity, which means equal selection rates across groups. So what could that mean in our scenario? Well, if you imagine our chef now has the head chef watching over their shoulder, and that head chef is really, he's going to apply a penalty. So every time the chef makes a recipe, or in our case, the model makes a version of the model that kind of has preference for males, a penalty will be applied. And so what eventually should happen is that the model should come out as being as accurate as possible or fair as possible. Now, what we're doing here, you see this grid size. We're giving it 31 attempts. So we're saying try 31 times to try and mitigate this model. So if we run this, what we should expect to see, if this works well, is a different outcome. So the first piece of output is our unmitigated model. You see we have the 7% prediction for female and 25.5% for male. Then we use grid search, which is now going to try 31 times to generate a different model. And we're going to use demographic parity as that constraint. So we're going to apply some constraints to it. Now what we see at the end of this is that the selection rate has dramatically improved. So this time we have 15% of the time female applicants have been predicted as high earners, and 15.28, so say 15.3% of the time male has been predicted as a high earner. So we've reduced that kind of bias from 17 or nearly 18% difference to just 0.3, which is pretty awesome. So grid search and demographic parity are the tools that we've used to reduce that bias. Now that's all well and good, but another responsible AI principles that we need to consider is, how did this work? Okay, and so how did it work? We can use additional open source libraries here. Now, what I'm going to show you are two libraries at the bottom. We have one called SHAP. Now, SHAP stands for Shapley Additive Explanations. And what it does, it helps us understand how each feature in the model, like age, education, hours worked, is influencing predictions. And it gives us a breakdown of the model's thinking. So it will say, for example, like age contributed to 10% to this particular score. Education reduced it by 3%. So it gives a kind of explanation of how things work under the cover. So what we'll do is we'll run this while I'm talking, and I should be able to show you some output hopefully in a moment. So let's give ourselves a minute while this is running. So you can see in the terminal window there, we have the unmitigated model. It's just running. We should then see the mitigated version. And what we'll get is this diagram. Now this shows us in the unmitigated model, the selection, the accuracy. So this time you can see like at the beginning, it's predominantly having a preference towards males rather than females. We then have the mitigated output, which is 15% and 15.3 essentially. And what that gives us is the mitigated model. Now, SHAP actually provides us with a breakdown of the model's performance. And what you'll expect to see is a breakdown of the model's thinking. So each one of these lines here is one of the features, one of the properties of the model that was used, and it can show you which features actually influence the predictions. So, for example, capital gain contributes to the score, whereas your marital status might have a negative impact. So that's what SHAP is actually doing for us. It actually gives us an overview of how the model made its decisions for a single person. So if a user asked why they were rejected, we can actually drill into that particular record and find out what happens there. Now, LIME works slightly differently. Let me show you the response from LIME. Now, LIME stands for Local Interpretable Model Agnostic Explanations, and that is a mouthful for me. But the idea is actually pretty simple. So it creates a simple interpretable model for just one decision, like a spotlight. It's agnostic, means it works even if your main model is complex or black box. And what we're doing is we're just picking one person and asking LIME, why did the model make this decision? And it returns a list of the top 5 features and how much each one pushed the result up or down. Similar to SHAP, but it helps us explain individual outcomes in a like a human readable way. Now, that's the end of this demo. Pretty brief, but what I wanted to kind of point out to you really is that we used, we created what we call an unmitigated model. We declared sex as a sensitive feature, and we split the data set 60% for training and 40% for testing. Now, the output of that was that we had bias, so a preference to males over females. In fact, the gap between male and female was nearly 18%. So 25% of the time, males were being predicted as high earners, and only nearly 8% of the time, females. We used grid search to try and train numerous times new versions of that model, and we used a constraint called demographic parity, and that applied a penalty every time the model had this bias. And we were then able to reduce that bias from nearly 18 percentage points down to 0.3. Now, it's not perfect, but it's very, very close, and it's a massive improvement. Now, one of the things we may have noticed with that is that the accuracy may have dropped a little, because we're now having a balance between fairness and accuracy. Moving on, we then used SHAP and LIME, which are 2 open source frameworks that allow us to actually create documentation and help us with that kind of explaining how decisions are made in the model. SHAP gave us that lovely view of kind of illustrating which features were adding to or influencing the decisions, both positively and negatively. So the combination of those three things, or four things, in fact, fairness, grid search, and demographic parity, then SHAP and LIME, we were able to not only train or create an unmitigated model, then mitigate it using demographic parity and grid search. Then we were able to actually document the model by using SHAP and LIME.